Secure boot feature ensures that a device only boots up with authorized software approved by original equipment manufacturer, whereas device debug security is designed to help prevent the debug capabilities of the devices from being exploited for malicious purposes. Secure boot uses cryptographic primitives to verify the boot components. Secure boot authentication process checks image integrity, validates associated certificate chain, and compares signing root certificates with the one programmed in device hardware root of trust. Secure boot enablement is a comprehensive process that covers every aspect of the enablement procedure, tool uses, and verification in the development environment. The following steps are involved in the secure boot enablement process: generate certificate and keys, sign the images, generate fuse configuration image, flash signed image and fuse blower image, and reboot the device, and verify the secure boot status of the device. Let's look at each step. The first step in this process is to generate the certificate and keys. Cryptographic keys and associated certificates need to be generated to sign the images. These cryptographic assets are owned by the OEM. Certificates are expected to be in X509 format, whereas the RSA or elliptic curve cryptography algorithms are used to generate digital signatures, and SHA-384 for hashing. Qualcomm Secure Boot supports both single and multiple root certificates in the certificate chain of the signed images. In the case of MRC certificates, the invocation and revocation of root certificates are supported via hardware fuses in Qualcomm Epi-ROM. These generated certificates and keys are used to sign the images. SecTool, a Qualcomm proprietary tool, is provided for signing and verification of the images, as well as generating the debug policy images to enable the debug capabilities on secure boot enabled devices. The next step is to generate fuse configuration to program hardware fuses in Qualcomm Epi-ROM. Once programmed, these put the devices in secure boot state. Secure boot features such as the image authentication, multi-root certificate support, rollback protection, and debug security are controlled via the security fuse configuration, which is programmed through the fuse blower images. It is essential to program the right set of fuses to enable secure boot and its features. After this, flashing tools are provided to flash signed images and the fuse blower image into device. On the next boot, after flashing, the touchstone reads the fuse blower image, programs the fuses, and auto reboots the device. From the next reboot onwards, the device only boots up with signed images. As the last step, secure boot status of the device could be checked from the boot up logs, or by reading secure boot status registers, or calling into TrustZone secure status check APIs. This completes the secure boot enablement process. Now let's look at the boot up process of secure boot enabled device. The device boot up starts from the app's primary bootloader, which is programmed in immutable ROM. Apps PBL is responsible for loading the XBL component images. The images loading and authentication logic is guided by the fuse configuration in QFP-ROM, which is programmed by the fuse blower image. After power on, the apps PBL is loaded. The apps PBL loads and authenticates XBLSec XBL from the EMC or UFS to the boot IMM and executes. Further, XBLSec passes the execution control to the XBL, which is an extended bootloader. XBL initializes the DDR, authenticates and loads MISC and XBL config images to the boot IMM, SSRM, AOP, CPU, CP images to the respective RAM region, and brings respective processes out of reset. XBL further loads and authenticates the TrustZone and hypervisor images to the PyMem memory area, and UEFI core image to the respective RAM region. Once boot images are all loaded, XBLSec transfers execution control to the TrustZone. TrustZone does cold boot and transfers control to the hypervisor and then to the UEFI core. During UEFI boot, the UEFI loads and initializes all the drivers loads and authenticates the device tree, and UEFI System Deboot Manager. System Deboot Manager presents a menu of boot options to control the boot flow and to enroll secure boot keys, and loads the bootloader or OS images selected by the user. System Deboot Loader loads and authenticates the Linux OS image and transfers control to it. In Linux kernel boot sequence, subsystem drivers such as video, GPU, NPU, etc. will call into the peripheral image loader, which will load the subsystem firmware and call into the Qualcomm TE to authenticate it and bring the subsystem out of reset. During device runtime, the HLOS TA client application requests the TrustZone to load the trusted application. The TrustZone will then load, authenticate, and executes the trusted application to which the client app can communicate with. Qualcomm Technologies provides SecTool to sign images, inspect them, and generate debug policy images to enable the debug capabilities of secure boot device. SecTool is scalable. It provides OEM with an option of using the default local signer or plug in their own HSM signer. In addition, another option would be to opt for Qualcomm licensed signing services, CAS. SecTool version 2 comes with Qualcomm Linux, a comprehensive package of software tools and documentation that features an executable binary. You can visit the Qualcomm portal and check the reference documents for more instruction on how to use the SecTool version 2. Our debug security feature provides a mechanism for controlled and authenticated debugging of secure boot enabled devices. Now let's go through some of these features in more details. We recommend disabling all invasive and non-invasive debugging on production devices, such as logging, memory dump analysis, hardware debugging using JTAG interface while enabling secure boot. The debug policy images need to be programmed in a device to enable its debugging capabilities. These images are generated using SecTool by passing security policy config XML and desired debug flags to secure debug utility of SecTool. These debug policy images need to be signed with the secure boot certificate and keys and are authenticated in the same manner as other secure boot images. SecTool provides an option to limit the use of debug policy and its application. To avoid the risk of accidental misuse, OEM can generate a debug policy even for a single device. You can find all the details on the various options supported and flags available using the SecTool Secure Debug Help command. You can also find the capabilities and application of SecTool in these documents. UEFI image is authenticated and loaded by Qualcomm Platform Secure Boot, which establishes the hardware root of trust for UEFI Secure Boot. UEFI Secure Boot helps to ensure that code executed by the UEFI firmware is secured and trusted. It authenticates OS loader, Linux image, system deboot, and DTV image, and ensures that the images are only loaded when signed and authorized by the OEM. The 4 stages of the UEFI boot flow include security stage, the driver execution environment or DXE stage, the boot device select or BDS stage, and finally the system boot stage. In the security phase, the root of trust is established and the hardware setup occurs. In the DXE stage, the UEFI driver execution environment is initialized. In the VDS phase, the boot device is selected, UEFI apps are initialized, and platform security setup take place. In system boot stage, the UEFI secure boot take place. The UEFI secure boot process prioritizes the platform security and integrity over systems running on UEFI based firmware. Upon successful authentication, execution control is transferred to high-level OS and its boot up begins. Key management is a critical aspect of cryptographic security. It's necessary to ensure that keys are generated, stored, exercised, exported, and access controlled in an execution environment, which is protected by platform secure boot. Effective management of keys are important to maintain a strong security posture of the product. Qualcomm Linux supports public key cryptography standard PKCS-11 specification for key management. It provides trusted application for key management, which executes in Qualcomm trusted execution environment, suitable for sensitive cryptographic operations, as both trusted application and Qualcomm TE are protected by the platform secure boot. Key management modules in Qualcomm Linux support industry standard symmetric and asymmetric algorithms and key sizes. For example, it supports different modes of block cipher such as AES, ECB, CRT, CMAC, etc., as well as public key cryptography such as RSA, ECC, etc., which can be used for encryption, decryption, wrap unwrap, sign, or verify. It also encompasses hashing algorithms such as MD5 and SHA of various digest sizes. Key management trusted application PKCS-11 provided with Qualcomm Linux is a cryptographic token interface standard compliant and executes in user space of trust zone to provide key management functionality to high-level OS user space client applications. CryptoKey library exposes key management interface to HLOS clients. It is shipped as a pre-built library in Qualcomm Linux, whereas trusted application for key management is provided in TrustZone as a component of Qualcomm Linux software. The Linux user space application can directly use the PKCS-11 interface through CryptoKey library, which uses global platform transport layer to communicate with PKCS-11 trusted application in TrustZone. To enhance device data security, Qualcomm Linux provides a storage encryption which supports transparent encryption of files and directories. Storage encryption uses the block cipher algorithm to protect data at rest by obfuscating it with the inline hardware crypto engine, ensuring the device data is only accessed by individuals or systems which have appropriate keys. Qualcomm Processor Security supports storage encryption with the inline crypto engine and a hardware wrapped key which provides better efficiency and enhanced key protection. The hardware-backed storage encryption feature allows provision of standard key ranging from 32 bytes to 64 bytes for content encryption of file names and file content with separate keys, and generation of 32-byte key identifiers. Qualcomm Technologies provides a dedicated crypto engine which is in line with secondary storage, UFS or eMMC. ICE or inline crypto engine enforces cipher operation on the data that is read or written based on its configuration and intent of the storage operation prepared by the storage stack. Our storage encryption uses FSCrypt, a lightweight encryption tool for encrypting files and directories at the file system level. FSCrypt is designed to work with both ext4 and F2FS file system, providing transparent encryption. This process is enhanced by ICE, which automatically encrypts and decrypts files as they are written and read. The Qualcomm Linux Security UFS storage driver is added to support the FSCrypt API. Developers can invoke the storage encryption functionality using the open source FSCrypt tool, which can be found on GitHub. The FSCrypt data path typically involves setting up the file system for encryption, creating and managing encryption policies for directories, ensuring keys are managed in a trusted execution environment. Developers need to first install FSCrypt, mount the file system with the encryption option, and initialize it on the target mount point. Next, they need to generate an encryption key for the directory and get it hardware wrapped. Once the hardware key is wrapped, it must be added to the directory. You will also need to create an encryption policy and add it to the directory. After these steps, you will have a foolproof encrypted directory where you can read and write data. Here is a sample set of commands which you can use to enable storage encryption on a directory using the fscrypt tool. Now we will discuss the Qualcomm platform's cryptographic offerings and cryptocores. The Qualcomm Processor Security provides native hardware support for the latest cryptographic industry and governmental standard. To perform cryptographic operations more efficiently, one or more instances of general purpose crypto engine, inline crypto engine, and pseudo random number generators are offered. These cryptocores are FIPS 140-2 certified. Let's have a look at the functionality of each of these cores. The GPC and ICE are the primary cryptocores. GPC is used for general purpose cryptography. It supports AES, DES, SHA, and HMAC crypto algorithm for various modes and key sizes, and is available for use in HLOS, modem, and trusted. ICE is used for inline encryption of storage to quickly encrypt or decrypt the files being written or read from the universal flash storage. The read-write operation to the UFS go through ICE for encryption or decryption. It is in line with the secondary storage device and supports AES 128-256, XTS, and ECB mode. Next, the pseudo random number generator or PRNG, which generates a random number stream compliant to FIPS standards. It uses an hardware-based noise sources to generate random bit stream. PRNG adheres to FIPS 140-2 and NIST SP 800-90A and 90V specifications. And lastly, we have the encrypted DDR supported by the PIMM hardware. It protects the runtime memory used by Qualcomm TE and trusted application running in Trustzone user space. Now let's look at OS security. It is critical for platform stability and its application. Kernel security is crucial for ensuring the integrity, confidentiality, and availability of the system. The Qualcomm Processor Security provides enhanced kernel security features for Linux implemented through platform hardware security mechanism. Let's elaborate on this. Key management is offered by a trusted application running in Trustzone, which supports PKCS HAS 11 standard for key management. It executes in the trusted execution environment and uses encrypted DDR region for its runtime operation. Similarly, storage encryption facilitates user data protection, which uses the key management module in the Trustzone for key generation, wrapping, and ICE drivers for inline crypto engine configuration, such as setting the encryption keys in ICE pipes, etc. It also provides file-based storage encryption, supports standard keys of 32-byte to 64-byte sizes, and FSCrypt. As part of boot authentication, UEFI Boot Manager authenticates the kernel image. In turn, the UEFI Boot Manager itself is protected by the platform Secure Boot, binding its security to device root of trust. Another important feature is kernel security hardening. Only an authenticated kernel can be trusted to enforce security hardening configuration and mandatory access control. To strengthen the security posture of operating systems, we must have enhanced kernel security features, which provides robust mechanism for protecting the integrity and confidentiality of the critical system components. The Qualcomm cellular connection security is crucial for edge devices having cellular connectivity. Attacks on cellular devices are rapidly increasing as devices have a greater presence in our daily lives. The expanding landscape for cellular attacks makes connected devices increasingly vulnerable to information theft and financial theft. Some of the most challenging cellular attacks that we face today are fake base station attacks such as IMSI Catcher or Stingrays, which make devices vulnerable to call and message intercepts, can downgrade and redirect victim devices from 5G, 4G to 3G, 2G. This exposes devices to fake SMS, fake emergency phishing, and privacy leak attacks, denial of service attacks, and partial service downgrade attacks. Understanding and addressing these cellular attacks is crucial to help protect connected devices from theft and exposure of private information. Qualcomm Technologies provides cellular connection security solution to help address these connection security concerns. Qualcomm Cellular Connection Security Solution augments 3GPP protocol security and is a scoring-based threat detection and protection solution that is designed within the Qualcomm model. Qualcomm Cellular Connection Security SDK is provided in HLOS for applications to receive threat detection like fake SMS, denial of service, location tracking, and more. Qualcomm Cellular Connection Security APIs, reference source code, and a sample application are provided to help developers get started. These APIs are available to Qualcomm developers under the Qualcomm Cellular Connection Security license.